All right. So the last couple sections of Chapter 5, we're going to talk about the polar coordinate system and polar equations. So the polar coordinate system is just another way to visualize relations. And so we've looked all semester long, we've been looking at how to visualize relations in the rectangular plane, but we can do this in the polar coordinate system as well. If you took trig, then you're already familiar somewhat with the polar coordinate system. Otherwise, here it is. So let's talk about polar coordinates. In the rectangular coordinate system, points are described in terms of their horizontal and vertical distances from the origin. So for example, the point -3, 2 describes the point 3 units left of and 2 units above the origin, right? So 3 units left and 2 units above the origin. In the polar coordinate system, points are described in terms of the angle that they make with the positive x-axis and their directed distance from the origin. So in this case, we call the positive x-axis the polar axis, and we call the origin the pole. I'm probably not going to use those terms. I always mess up and just call them the x-axis and the origin. But for your own reference, right? It's technically the polar axis and then the pole. So let's just practice plotting some points. So let's do the point 3, 150 degrees. So that means we're going to come out to 3 and then go around to 150 degrees, right? So there's 90 degrees. 180 degrees would be too far. I think 150 degrees is 30 less than 180, so it's right there, right? Oh, hold on a second. 1, 2, 3. Yeah, right there. So there's 3, 150. So there's part A. For part B, we would do 1, 3 pi over 2. So 1, 3 pi over 2. Pi over 2, pi, 3 pi over 2 right there. For part C, we would do 0 pi over 4. Well, 0 pi over 4 is just going to leave us right here at the pole. And then for part D, we have 2, -60. 1, 2, -60 would put us, so we'd go in the opposite direction, right? We're not going to go counterclockwise, we're going to go clockwise down to -60. So this one is part D. Okay, let's do some more. It says plot the following points with polar coordinates. So 4, 30. 1, 2, 3, 4, 30 degrees, right there. 4, -30. 4, -30 is right there. So this is A, B. -430. -430. Well, so for -430, we would come out to 30 degrees, but then we would go in the negative direction. 1, 2, 3, 4. Right? So there's part C. And then part D is -4, -30. Okay, so for -30, we would come down to -30 degrees. And then for -4, we go in the opposite direction. 1, 2, 3, 4. So there's part D. Okay, here's another set of examples. It says, show that the following polar coordinates describe the same point. Okay, so 2, 11 pi over 6. So 11 pi over 6. So this is pi over 6, 5 pi over 6, 7 pi over 6, and I think this one is 11 pi over 6. And we're going to come out to 2. So that's part A right there. 2, 11 pi over 6. Now part B is asking for 2, -pi over 6. So 2, -pi over 6. Sure enough, same point. Part C is asking for -2, 5 pi over 6. So 5 pi over 6 is right here. And then for -2, we go in the opposite direction, and sure enough, land at the same point. Then finally, -2, -7 pi over 6. So -7 pi over 6, there's pi over 6, -pi over 6, -5 pi, -7 pi over 6, -2. Okay. The moral of this story is that in rectangular coordinates, each point has a unique representation. That's not true in polar coordinates. In polar coordinates, each point has an infinite number of ways that it can be described. Okay. One of the things that we want to be able to do is convert back and forth from rectangular to polar and from polar to rectangular. So to convert from rectangular to polar is basically the same exercise as writing a complex number in polar form. Okay? That is, we have to find theta and we have to find r. So let's practice. Let's convert the following rectangular coordinates to polar coordinates. Let's make sure that r is a positive number and that theta is between 0 and 360. That way we'll all get the same answer. Okay, but let's do this. So the point -1, -1. Well, first of all, r is going to be the square root of x squared plus y squared. Right? Same relationships as what we had for changing a complex number into polar form. So r is the square root of 2. And then theta satisfies tangent theta is y over x. So tangent theta is 1. But careful now, which quadrant are we in? Right? -1, -1 puts us in quadrant 3. Right? So there's theta right there. So obviously theta is not going to be 45 degrees. Theta would have to be 45 degrees plus 9 degrees. So it would have to be 2... what was I about to say? Theta would have to be 225 degrees. Holy schmoly. I'm tired. You know what? At this point, I'm recording this video right now, but I've already been recording videos today for about 3 hours, and I had a Zoom meeting that lasted for like an hour and a half. Anyway, my brain is a little bit fried. But here we go. Okay, so theta is... we said 225 degrees. So then the rectangular coordinates for this would be r theta. Okay, and so that's how that works. Go ahead and give the video a pause and see if you can do part B on your own. Okay, here's my solution. Okay, theta is in quadrant 2. So I'm going to do tangent inverse of -√3. And then add 180 degrees. So 120 degrees. Okay, so there's the polar coordinate. That corresponds to this rectangular point. Okay, so that's how we go from rectangular to polar. If we wanted to go from polar to rectangular, then we use these relationships, which should be fairly familiar to us. Let's just draw a picture to convince ourselves that that's really the relationships that we would have. So if we had some point r theta, and we wanted to describe this in terms of its horizontal and vertical distance from the origin, right? This would be r, this would be theta. Then we can say, well, cosine theta is x over r. Right, so we say cosine theta is x over r. Well, so that implies that r cosine theta equals x, right? And in a similar way, we could say sine theta is y over r, so that y equals r sine theta. Okay, so if we want to convert a polar point into a rectangular one, well, then we just use x equals r cosine theta and y equals r sine theta. So in this case, we would say x equals r cosine theta. Cosine of 60 degrees is 1/2, right? So this would be -3/2. And then y equals r sine theta. Sine of 60 degrees would be √3/2. So this is going to be -3√3/2. So the rectangular point would be -3/2, -3√3/2. See if you can do part B. So go ahead and give the video a pause. Okay. So this is going to be, x is going to be r cosine theta. Cosine -pi/4 is √2/2. Y is going to be r sine theta. Sine -pi/4 is -√2/2. So the corresponding rectangular point is √2, -√2. Okay. Instead of going point by point, we can actually convert entire equations from rectangular to polar or from polar to rectangular. And the strategy is pretty much the same. So for example, if we want to convert this rectangular equation into polar form, well then we would just make the replacement x equals r cosine theta and y equals r sine theta, and then simplify if we can, right? So we would get r cosine theta minus 1 squared plus r sine theta plus 1 squared equals 2. Usually we like to get this as r equals some function of theta, right? So r equals something going on with theta, maybe a cosine theta or a sine theta or something. But the point is, we like to be able to solve for r if possible. So let's try to solve for r now that we've made this replacement. But before I do that, let me just point out that actually what we have here is already in polar form, right? This is in polar form now, so our work is done. What I'm going to do from this point on is just simplifying, right? I'm just going to try to solve for r if I can. So let's see, if I square this first group, I'm going to get r squared cosine squared theta. When I multiply the outsides, I would get negative r cosine theta, and then I would get it again, so that's negative 2r cosine theta. And then negative 1 times negative 1 is positive 1. If I FOIL out the second group, I'm going to get r squared sine squared theta plus 2r sine theta plus 1. Okay, let's see if I can simplify this at all. First of all, I can put the r squared cosine squared and the r squared sine squared together and factor out the r squared. I can also take out a 2r, I guess. I can factor out a 2r, and I'm left with cosine theta plus sine theta. I don't know if that's going to be particularly useful. And then 1 plus 1 is 2. Well, I can move the 2 over, right? But here's what I wanted to point out, is that cosine squared plus sine squared is just 1. So now I've got r squared minus 2r cosine theta plus sine theta equals 0. So remember, it's my goal to solve for r. I could divide through by r, get r minus 2 times cosine theta plus sine theta equals 0 divided by r, which is just 0. And then move that thing over to the other side to get r equals 2 times cosine theta plus sine theta. And that's it. So that's kind of interesting. Okay. Anyway, you were done at this step, technically, right? The rest of it was just seeing if you could simplify and solve for r. Okay, so that's how we go from rectangular to polar form. We literally just replace all of our x's with r cosine theta, and we replace all of our y's with r sine theta. That should be a piece of cake compared to what we were doing in the previous section, right? or not the previous section, but in 5.4, right? Rotation of axes. To go from polar to rectangular is a little more difficult. These are some replacements that could come in handy, and hopefully they all make sense to you, right? Like we know that tangent theta is y over x. You know that x is r cosine theta, y is r sine theta. We also know from the Pythagorean theorem that x squared plus y squared equals r squared, right? So all of those things could potentially come in handy. I'm going to give you 4 examples. Excuse me. I'm going to give you 4 examples because I think between the 4 examples I'm going to give you, you'll see pretty much all the standard tricks. Okay? So starting with r equals 5. If I want to change this into a rectangular form, I need to make some kind of replacement. I could say, for example, I could say r is x over cosine theta. That'll get rid of the r, but then it introduces a theta into the mix. And I don't want any r's or thetas. I only want x's and y's. Another thing I could do maybe is multiply both sides of this equation by r. Then I get r squared equals 5r. The r squared I can replace with an x squared plus y squared. But see, then I still have an r on the right-hand side, so that doesn't quite do it. But thinking along those same lines, maybe what I can do instead is just square both sides, right? If I square both sides, I get r squared equals 25. And r squared I can replace with x squared plus y squared. And then I've done it, right? Now I don't have any r's, I don't have any thetas. I just have x squared plus y squared equals 25, which, by the way, is a circle with radius 5. Interesting, right? It's a circle with radius 5. R equals 5. Okay, we'll talk more about that in a second. Let's do part B. Theta equals negative pi over 3. So the standard trick whenever you're confronted with something like this is to just go ahead and take tangent to both sides, right? If theta equals negative pi over 3, then certainly tangent theta equals tangent of negative pi over 3. Tangent theta I can replace with y over x. Tangent of negative pi over 3 is negative root 3. So that's in rectangular form now, right? I don't have any r's, I don't have any thetas. It's in rectangular form. If I wanted to, I could multiply through by x. So then you can see that you just get this straight line. It's a straight line with slope negative root 3. So you're going to go down approximately 1.7 and then over 1, right? So there's that one. R equals secant theta. Well, secant theta is 1 over cosine theta. I can multiply through by cosine theta to get r cosine theta equals 1. And then look at that, right? R cosine theta is just x, right? So I get x equals 1. And there's my rectangular equation. That's just a vertical line. And one more. R equals 2 sine theta. I can square both sides, get r squared equals 4 sine squared theta, but I don't know how I'm going to get rid of the sine squared theta at that point. So maybe instead I multiply through by r, right? So I'm going to multiply both sides by r, and I get r squared equals 2r sine theta. Now r squared I can replace with x squared plus y squared, and r sine theta I can replace with y, so this is 2y, right? This whole thing just becomes y. It's 2y. So there you go. This is some kind of circle, right? I could complete the square on it. I wasn't really asked to do that, but whoops. Let's do it. X squared plus y squared minus 2y equals 0, except that I'm going to add 1 to complete the square. So I'm going to get x squared plus y minus 1 squared equals 1. So it's a circle with center 0, 1, and radius 1. It's pretty nice. Okay, So we've talked about how to work with polar coordinates, how to plot polar points. We've talked about how to switch back and forth between polar and rectangular coordinates. We've talked about how to switch back and forth between polar and rectangular equations. The other thing that we're going to want to do, and we're going to spend a lot of time doing this in the next section, but for now I just want to get used to plotting some points, because the other thing we're going to want to do is learn how to graph polar equations. Okay? So let's say that we have this polar equation, r equals 2 plus 2 sine theta. As I said, in the next section we'll talk in greater detail about how to do these things. For now I'm just going to plot some points. So I'm going to plug in some things for theta and then see what I get for r. So for theta I could plug in, 0, 30 degrees, 45 degrees, 60 degrees, 90 degrees, and I could continue to do that all the way around. So 120, 135, 150, 180. That'll get me halfway around. I want to get all the way around though. So I'll tell you what, I'm going to skip some. I'm going to do 180, then I'm just going to do 225. I'll come back and fill in some blanks if I need to. 225, 270, and then, oh, what is this? 270 plus 45, so 315, right? Okay, I'll come back in and fill in some more if I need to. But I'm just going to plug these in here and see what I get. So 2 plus 2 sine theta. So when theta is 0, I get 2. When theta is 30 degrees, I get 3. When theta is 45, I get root 2 plus 2, which is approximately 3.4. When theta is 60, I get root 3 plus 2, which is approximately 3.7. When theta is 90, I get 4. And then I should have mirror images, right, for a while. 150, should be back down to 3, and then 180, I should be back at 2. Wonder what's happening at sine of 225. I get 2 minus root 2, that's about 0.5, or 0.6 at 270. I get 0, that's interesting, and at 315, oh, at 315 I'm back at about 0.6. Okay, so let's plot these points, and like I said, if I need to come back and fill in some blanks, I will. But let's plot what we've got. So I've got 0, 2, 33, 1, 2, 3, so 30 degrees, radius 3. At 45 degrees, I'm at 3.4, 1, 2, 3.4. At 60 degrees, I'm at 3.7, 1, 2, 3.7. At 90 degrees, I'm at 4, 1, 2, 3, 4. And then it starts to come back down, right? So like that, like that. Where was I at 150 degrees? 3, 1, 2, 3. And then at 180 degrees, I'm back out at 2. Okay. At 225 degrees, I'm at 0.6, so that's right about there. At 270 degrees, I'm at 0. And then at 315 degrees, I'm out at 0.6. Now, the thing about polar equations is that you should connect the dots in order, right? Right now, it may look like just a bunch of dots on the page, and you may not know, should I go here, and then there, and then there, and then there, right? But connect them in order. We started here, and then we went around this way. So I think the picture we get looks like this. Okay, something like that. We could verify this by plugging in something like 210 degrees here, right? If we plugged in 210 degrees, what would we get? We would get 1. So 210 degrees, 1. Yeah, sure enough. Right? So that looks about right. Okay. So that's how that works. Let me show you another one. This one is going to be a spiral. They call this the Spiral of Archimedes. So Spiral of Archimedes. Let's plug in some things for r and theta. We should plug in positive and negative values. So I'm going to plug in some negative values over here and some positive values over here. So if theta is, let's say negative 45, or actually, you know what? It's kind of dangerous to use degrees when you're doing polar coordinates. It really needs to be in radians. So let me do negative pi over 4, negative pi over 2, negative pi, negative 3 pi over 4. Hold on a sec. 2 pi over 4, negative 3 pi over 4 goes here, right? Negative pi, negative 5 pi over 4, negative 3 pi over 2, negative 7 pi over 4. And then, I'm just going to start getting bigger and bigger. So negative 2 pi, negative 3 pi, negative 4 pi, and so forth. Let's see about how much this would be, right? So this is so r is just exactly equal to theta. So what is pi over 4? It's about 0.8. Pi over 2 is about 1.6. 3 pi over 4 is about 2.4. Pi is about, I should have been able to do that one in my head, huh? Pi is about 3.1. 5 pi over 4 is about 3.9. 3 pi over 2 is about 4. Oh, these should all be negative, by the way. These should all be negative. This is about negative 4.7. 7 pi over 4 is negative 5.5-ish. 2 pi is like negative 6.3. Negative 6.3. 3 pi about negative 9.4. 4 pi is about negative 12.6. Okay, now the good news is that I don't need to do this again for the positive angles over here because their values are all going to be the same. They're just going to be positive, right? So let's say 2 pi, 3 pi, 4 pi. All right, so it's going to be about 0.8, about 1.6, and so forth. At 2 pi, it's about 6.3, about 9.4, and about 12.6. Okay, so let's see if we can plot these things. Let's plot the negative ones first. So at negative, first of all, at 0, I'm at 0. Okay, and at negative pi over 4, I'm at negative 0.8. So that would be maybe right about there. Right, negative pi over 4. At negative pi over 2, I'm at 1.6, or negative 1.6, so right about there. At negative 3 pi over 4, I'm at negative 2.4, 2.4. At negative pi, I'm about negative 3.1, 3.1. At negative 5 pi over 4, I'm at negative 3.9, 3.9. And then at negative 3 pi over 2, 4.7, 1, 2, 3, 4, 5, 6, or 1, 2, 3, 4.7. Anyway, you can see that as theta gets bigger and bigger in the negative direction, the bigger and bigger r is going to get, of course, right? So at negative 7 pi over 4, I'm at negative 5.5. 1, 2, 3, 4, 5.5. At negative 2 pi. At negative 2 pi, I'm at negative 6.3. 1, 2, 3, 4, 5, 6.3. Then at negative 3 pi, I'm at negative 9.4. 1, 2, 3, 4, 5, 6, 7, 8, 9.4. And then 12.6. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12.6. So somewhere way out here. Anyway, so in the negative direction, it looks like I'm going like this, right? So it's this spiral. In the positive direction, I think I'm going to be going in the opposite direction. So I have pi over 4, 0.8. Pi over 2, 1.6. 3 pi over 4, 2.4. 1, 2.4, right? Maybe I should plot what was happening in the negative direction before I confuse myself. I'm already confusing myself. But it was looking like this, right? That's what it was looking like in the negative direction. In the positive direction now, it looks like it's doing kind of the opposite, right? So it's going this way. So it looks like it's going to be a mirror image. 1, 2, 3. So 1, 2, 3. Right, so pi 3.14. So it's going to go down like that. And so forth. So at so let me cut to the chase and do 3 pi over 2. 3 pi over 2 is going to be 4.7. 1, 2, 3, 4.7. Yep, so this goes there. At 2 pi, it's going to be at 6.3. 1, 2, 3, 4, 5, 6.3, right about there. Okay. At, well, and then it's going to keep doing this, right? So oh, well, this is 2 pi, this is 3 pi, so at 3 pi I'm going to be at 9.4. 3, 4, 5, 6, 7, 8, 9.4. And at 4 pi, I'm going to be at 12.6, so somewhere kind of out here. Right, anyway, so this is the picture you get. So it's this spiral, it's this double-edged spiral. I want to take you to Desmos and just show you a couple of these graphs. So first of all, let me show you how to get to polar equations in Desmos. So the default setting in Desmos is to open up into a rectangular coordinate system like this. If you want to make it polar, then click on this little wrench and then make it polar. And then if you want to make these numbers, you know, well, actually it already is in radians, so never mind. So this is good. So if I want to do r equals theta, then I would say r equals theta. And there you go. Notice that it's starting at 0 and going to 12 pi, so it's only giving me the positive half of the spiral. If I want it to give me the negative half of the spiral as well, then I can just make it start at negative 12 pi. And there, now it looks like what we drew. Pretty cool, right? It's stopping at 12 pi, but theoretically, I mean, it could go on forever and ever. So there's what that one looks like. The first one we did was r equals 2 plus 2 sine theta. Okay, so that looks like what we did on number 8, part A. And these things can get really complicated and make really cool pictures. So I'm going to type in this polar equation that I say to type into Desmos down here. Let's see what we get. if we do r equals 3.5 minus 1.5 times the absolute value of cosine theta. Okay, that looks kind of cool. Times the square root of 1.3 plus the absolute value of sine theta plus cosine 2 theta. I stole this from somebody. I didn't come up with this myself. Ah, look at that. And then plus 0.7 cosine 12.2 theta. Ooh, look at that. That's a pretty picture. Anyway, so these things can get pretty cool looking. You can have a lot of fun with these polar equations. In the next section, we're going to talk more in depth about graphing polar equations.